welcome to today's presentation on photoelectric effect. What is that? Photoelectric effect. Let's see here. What is the meaning of photoelectric effect? The emission of electrons from a metal surface which is exposed to light such as UV light, X rays, gamma rays, visible rays, IR rays, which means electromagnetic waves, of suitable frequency is called photoelectric effect. The emitted electrons are called photoelectrons, and the resulting current is photoelectric current. You can see here, this is a metal surface. Upon this metal, this is a metal surface. Upon this metal, a suitable frequency of light such as UV, X-rays, gamma, visible, which we consider as incoming electromagnetic waves, when they incident on metal surface with suitable frequency, then electrons are emitting, and this is called photoelectric effect. Because of photoelectric effect, the current generated is called photoelectric current. So that is about photoelectric effect. Non-metals, liquids, gases also show this effect, but it is limited to certain extent. So we will observe the photoelectric effect exclusively on metal surfaces. In a small or narrow range, we can able to observe on non-metals, liquids, as well as gases, but this is a limited character. In other way, we will consider the phenomena which electrons are emitting from a surface of metal when a suitable light with a frequency of suitable fall on metal surface, then electrons are emitting. That is called photoelectrons. That is what? Photoelectrons. The current generated is photoelectric current, and this effect we call photoelectric effect. This effect shows, what is the important? Shows that light can behave not only wave character, it also proves that light behave as a particle nature. It given experimental proof for the nature of light in particle manner. Earlier we believed that light is a nature of wave, but photoelectric effect confirm that light is a particle nature. So these particles we call as photons. They will be considered as photons. This study of photoelectric effect played a major important role in quantum theory. It also played very important role in quantum theory. See here, electrons are a suitable frequency of light incident on a metal surface, then the metal surface emitting some electrons, then this is called photoelectrons. In the photo, because of these photoelectrons, whatever current is generated, that is called photoelectric current. And here this experiment proved that one confirmed that light not only wave nature, it is also in the particle nature, and these particles are known as photons. And this photoelectric effect is given a solid foundation to the quantum theory. Clear? What is the basic idea related to this photoelectric effect? Simple thing. Light energy. What is that? Light energy is changed to emission of electrons. This is a simple one. Light energy changed to emission of electron. This is a basic idea related to photoelectric effect. Light energy, in simple terms, light energy is converted to emission of electron. This is the basic idea for photoelectric effect. When light strikes a metal surface, this is a metal surface, this light striking this metal surface, if the light has enough energy, then electrons are released. If the light has enough energy, then electrons will be released. The energy of light depends on, see, this energy of light depends on frequency. The energy of light depends on frequency. Higher frequency producing higher electron, that means higher frequency of light emitting higher electrons. So obviously the simple representation, light energy converted to emission of electrons. What is that? Emission of electron. This is not a single day discovery. This photoelectric effect is developed by many scientists, in that the first one is about early observations by, that is, Hertz. What is that? Hertz. Then after Halbach, Thomson, then classical theory, finally Albert Einstein. So like that, there are many persons are involved in producing successful concept related to photoelectric effect. The first one, that's about Heinrich Hertz. In the year 1887, Heinrich Hertz first observed the photoelectric effect while experimenting on electromagnetic waves. So, who developed the photoelectric effect? So that's about in the year 1887, Heinrich Hertz, when he was working on electromagnetic waves, he noticed that when he works on electromagnetic waves, he noticed that ultraviolet light, ultraviolet light helped electric spark, so that means ultraviolet light producing electric spark. What is that? Electric spark between two metal electrodes, between two metal electrodes, this was the first evidence that light could affect electrons in metal. So that is Heinrich Hertz concept. What is that? when it was working on electromagnetic waves. When UV light exposed on a metal surface between two electrodes, it observed that one a spark, and finally it was confirmed that first evidence that light could affect electrons in metals. So that's about the Heinrich Hertz proposed in the year 1887, the first person who developed photoelectric effect. Next, that is experimental studies by Hallwatch and Thomson. Hallwatch and Thomson. Hallwatch shows that metals lose negative metals. What is that? Metals lose negative charge when exposed to UV light. When exposed to UV light. So that's about Hallwatch experiment. Hallwatch experiment is what? Hallwatch shows that metal lose negative charge. Metals lose negative charge when exposed to ultraviolet light. Later, J.J. Thomson proved that emitted particles are known as electrons. Emitted particles are known as electrons. Here, what? See, Hallwatch, while he was doing some experiment, he found that one on a metal surface, if UV light exposed, electrons, that means negative charge. See, metals lose negative charge, that means metals are releasing some negative, metals are going to lose negative charge. This negative charge named as electrons by J.J. Thomson. By Thomson. So this is another milestone in development of photoelectric effect. So here, so like and Albert Einstein, that we will see in coming slide. So like that Albert Einstein proposed Albert Einstein equation based on quantum explanation in the year 1905. That is the reason he was awarded Nobel Prize. Let's see, what is the experimental setup for the photoelectric effect. See, this is all about the experimental setup for the photoelectric effect. See, this is a we have two plates, one cathode plate, another one is anode plate, and both the plates were connected to the external source. See, there is a window that is we call W, and this window is helpful for what? For incoming of UV light. And there this one this circuit is consists of plug key, voltmeter and ammeter. Ammeter is used to measure current, voltmeter to used to measure the potential, plug key is used to supply the power. So here C is a metal cathode plate, A is anode plate, W is called quartz window. Let's see here the components. C cathode plate, A anode plate, K plug key, V voltmeter, this one microammeter. So this is about external source. So this is about the experiment setup for the photoelectric effect. Let's see here, when UV light falls in cathode plate, then electrons are releasing, electrons are emitting, and which are transmitting towards anode plate from cathode. And these electrons, which are generated or produced because of this UV light, then these electrons are called photoelectrons. Photoelectrons are emitted and they are transmitted towards the anode plate because anode plate is attracting it's the positive terminal plate where cathode is negative terminal plate. So these negative charged electrons are attracted by this positive terminal anode. Like that, between cathode and anode, current is generated and that we call as photoelectric current. That means photoelectric current flows between cathode and anode plates and that was measured in microamperes by using of ammeter. And where the observations are concluded from this experiment. Finally, from this experiment, the observations are concluded as intensity is proportional to current. That means at a fixed frequency, photo current increases linearly with the intensity. That means if you increasing intensity of photons, then for electric current also increases. Then potential saturation. Current rises with the positive anode potential until a saturation means was stable. A stopping potential versus reduced current is zero. That means intensity does not affect it because of potential. Then third observation from experiment. Higher frequency, higher stopping potential. Saturation current remains same for different frequencies. Threshold frequency. Below threshold frequency nu naught, no emission occur regardless of intensity. Nu naught depends on metal, that means nature of the metal. So these are the four conclusions, observations made from experimental procedure. Let's see briefly. So here, effect of intensity of incident light on photoelectric current. So let us consider this graphical representation on x-axis and y-axis. On x-axis intensity of incident light and y-axis photoelectric current. See, there is a linear curve is observed. That means what? For a fixed frequency, the photoelectric current increases linearly with increases in intensity of incident light. That means if incident light increases, photoelectric current also increases. And this shows proportionality relation between intensity of incident light and photoelectric current. And second observation, effect of potential on photoelectric current. For a fixed frequency, the incident light, the photoelectric current increases with increasing potential applied to the anode. That's anode is nothing but what? Positive. When all the photoelectrons reach the plate A anode, current becomes maximum and this is known as saturation current. That means when we are connected to negative terminal to the cathode, positive terminal to anode, then all the negative charged electrons are transmitted or attracted by positive terminal of the anode. Then at certain position at an instant, that current is maximum, thereafter no increasing current, and that level we call as saturation current. What is that? Saturation current. So this is about this stable curve we call saturation point. When the potential decreased, the current decreases but does not becomes zero at potential. This shows that even in the absence of accelerating potential, a few electrons manage to reach plate on their own due to their kinetic energy. When negative potential is applied to plate A with respect to plate C, for the electric current becomes zero at a particular value of negative potential called stopping potential or crop potential. Intensity of incident light does not affect stopping potential. This is you need to understand. This is a major fact. There is no relation between intensity of incident light and stopping potential. Earlier we discussed that cathode and anode. Cathode is connected to negative terminal, anode is connected to positive terminal. So that is the reason maximum current is generated, and this limit of maximum current we call as saturation current. But when we reducing potential, at the same time when we shifted this anode is negative, cathode is positive. So gradually these electrons, see this is negative and this is positive, so that these electrons may not slowly they reach anode plate in delay manner. So that is the reason photoelectric effect is reducing but not zero. Even though when we shifted the terminals, because of the electrons kinetic energy, they lately reaches to plate A. That means negative potential is that means photoelectrons are reaching to the anode plate in delay manner at an instant potential. These electrons are not reached to the anode plate A. At what potential these electrons are not reached to the plate A, and that potential we call as stopping potential or cut off potential. Third observation from experiment: effect of frequency of incident light on photoelectric current. So for a fixed intensity of incident light, the photoelectric current does not depend on the frequency of incident light, because photoelectric current simply depends on number of photoelectrons emitted and in turn on number of photons incident, not on energy of photons. So here effect of frequency of incident light on photoelectric current. So for intensity of incident light, so the photoelectric current does not depends on frequency. Remember, photoelectric current does not depends on frequency. That your frequency of incident light, this you have to remember. You have to take the serious note on this one. The photoelectric current does not depend on the frequency of the incident light. That's it. Then effect of frequency of incident light on stopping potential. See, stopping potential. For a fixed intensity of light, incident light, the photoelectric current increases and is the saturated with increasing in positive potential applied to the anode. See, earlier we discussed cathode anode. This is negative terminal, this is the positive terminal. So that is the reason these photoelectrons are reached to the plate A. So that is the reason maximum current is producing, and that's about saturation current. So here, this saturation current is same for different frequencies of the incident light. When potentially decreases, that means when we shifted the terminal, this is positive and this is negative. Photoelectric current decreases to zero by different stopping potential for different frequencies. So remember here, saturated current is same for different frequencies. Here, different stopping potential for different frequencies. Here, saturation current is same. Saturation current is same for different frequency. Here, different stopping potentials for different frequencies. That see, nu 1, nu 2. Saturation current is same, but the frequency is changed. Higher frequency, higher stopping potential. Higher frequency, so higher stopping potential. And finally, threshold frequency, the graph between slow stopping potential and frequency. It shows that there is a minimum value of frequency called threshold frequency, below which photoelectric emission is not possible. However, higher the intensity of incident light may be. It depends on natural metal emitting photoelectricity. To get electrons emission, there should be some minimum frequency. The minimum frequency which required to eject the electrons, and that frequency we call as threshold frequency. Threshold frequency, it depends on the nature of the metal. For cesium, for sodium, for zinc, other it is changed to metal. So you can see that it means observations in rough graph. So this is about the photoelectric effect and intensity. This is about for the intensity of light with the incident current. That is about the stopping potential and collector plate potential I1, I2, I3. I3 is greater than I2, I2 is greater than I1. You can see here. And stopping potential versus collector plate potential. See here, this is stopping potential, collector plate potential. This is stopping potential, collector plate potential, and with respect to the saturation, you can see here the graph relations. Photoelectric, see, photoelectric current with stopping potential, photoelectric effect with stopping potential. But here, in terms of the frequencies, here in terms of the intensities, this is the in terms, okay, sorry, I will show that one. This is related to the saturation current position. This is related to the stopping potential. Say I3, I2, I1. Here nu 3, nu 2, nu 1. And this is about the threshold frequency, stopping potential versus frequency, and that's about I will show here stopping potential. This is metal A and this is metal B. So here we know very well the maximum energy, it is equal to, as we know very well, H nu is equal to H nu naught plus K max. K max equal to AV naught. So that H nu equal to H nu naught plus AV naught. So this is just like, you can check what is that, H nu naught equal to H nu minus AV naught. So here the simple one, H nu naught is nothing but just like a phi function. So here nu naught equal to, you will see nu, you can take by with respect to E. So here This is h nu naught is nothing but phi. So I can say that is h by, okay, no problem. I mean, 1 second. See, general here, h nu equal to what? H nu naught plus k max. K max is nothing but ev naught. So h nu equal to h nu naught plus ev naught. So h nu naught is nothing but what? This is h nu, and this is about phi naught. Phi naught equal to h nu equal to phi naught plus ev naught, then h by e into nu plus phi by e plus here e by e out, so e naught, so you will get nu naught. So that is about y equal to mx plus c formula. So that means it is indicating about the slope character. What is that one? It is indicating about slope nature. Y equal to mx plus c. Y equal to mx plus c. Okay, then last related to photoelectric emission, that is threshold frequency, current is proportional to intensity, maximum kinetic energy is proportional to frequency, instantaneous in 1 to 1. What is threshold? No emission below threshold frequency. However, higher the intensity, higher threshold frequency. Photoelectric current is directly proportional to intensity of light. Maximum kinetic energy is proportional to frequency. Maximum kinetic energy of photoelectrons is proportional to the frequency and independent of intensity. Instantaneous emission is instantaneous, and one photon eject one electron. Let's see briefly. Loss of photoelectric emission. For a given substance, there is a minimum value of frequency of incident light called threshold frequency, below which no photoelectric emission is possible. However, the intensity of incident light may be. So here we need certain frequency to eject the electron, and that frequency is about threshold frequency. The number of photoelectrons emitted per second, which is nothing but photoelectric current, is directly proportional to intensity of incident light, provided the frequency is above the threshold frequency. And third last, the maximum kinetic energy of photoelectron is directly proportional to the frequency, provided to the frequency is above the threshold frequency. So threshold frequency is mandatory. Below threshold frequency there is no emission of electron. The maximum kinetic energy of an electron is independent of the intensity of incident light. So that maximum kinetic energy of an electron is independent of intensity of incident light. And fifth one, the process of photoelectric emission is instantaneous. That means as soon as the photon of suitable frequency falls on substance, it emits photoelectrons without any delay. And sixth one, photoelectric emission is 1 to 1. For every photon of suitable frequency, one electron is emitted. Einstein photoelectric effect. See here, this is the last development related to photoelectric effect. Einstein explained the photoelectric effect, and it was discovered by H in the year 1887 when working on electromagnetic waves. So Einstein explained the photoelectric effect by assuming light is a quantized in packet. This is quantized, we call photon. Later they named as photon. So given a relation that is about E equal to h nu minus h nu naught, and where E is nothing but 1 by 2 mv square equal to h nu minus h nu naught. So here, to eject an electron, frequency nu must exceed the threshold frequency. Higher intensity, more electron. So that is depends on frequency, and that frequency we call threshold frequency. So here, this is a metal surface. So photon of h nu is incident on a metal surface. Then this will associate with some energy, and that's about the kinetic energy then it releasing for an electron. So here a photon of energy h nu is absorbed by an electron part to overcome the work energy. So here the work function is h nu naught. So here the photons of h nu is incident and emitted surface. Then the photon of energy it is converted to the work function. Then after it is ejected some electron by associated with some energy, that's about the kinetic energy. So here h nu equal to h nu naught plus, so here h nu equal to work function, that is about what, phi, plus these electrons are emitted with energy, that is about the kinetic energy k. So phi is nothing but h nu naught phi, and kinetic energy is 1 by 2 mv square max. So finally here after reshuffling 1 by 2 mv square max equal to h nu minus h nu naught, where h is the common, so h of nu minus nu naught. So that's about where h is nothing but Planck constant value 6.6 into 10 to the power minus 34 watt second square or joule second. Nu is frequency, that's in hertz. H nu naught, that is work second or joule. So here Albert Einstein explained photoelectric effect discovered by H in 1887 by assuming that light is quantized in quantities that later became known as photons. The kinetic energy of ejected electron 1 by 2 mv square is equal to h nu minus h nu naught. So that's about, see, metal other than alkali metals. See, UV light incident on metal surface, then photoelectrons are produced. Visible light when incident on metals other than alkali, no photoelectric effect. Visible light when incident on alkali metals, photoelectrons are emitted. So that's about the UV visible light characters related to photoelectric effect. So here what we believed earlier, see, brighter light means electrons with more kinetic energy. This is expected, but that was brighter light means more electrons, so same kinetic energy. Dim light, delayed emission, but here even faint UV light is producing instantaneous emission. This is myth, this is fact. Myth, what expected from experiment, but finally what we found by the experiment. Frequency wouldn't affect the electron energy, but here higher frequency, higher electron energy. Einstein resolved these discrepancies using Planck idea. Light comes in a fixed quanta which we call photons, that was shut out by the Einstein and fixed by his experiment, that is Einstein photoelectric effect. Applications of photoelectric effect. See, safety systems, industry, media, entertainment, science, measurements. See, in safety system, atomic fire alarms, burglar alarms, and automatic street light we're using photoelectric effect. TV scanners, cinema sound refraction, and light emitters in film industries. In industry, measuring paper thickness, detecting flaws in finished goods, for electric shorting, and for accounting. Science and measurements. Astronomy, opacity measurements of solid, liquids, forms temperature control, and meteorological. We use this for electric effect. Applications of photoelectric effect briefly: atomic fire alarm, atomic burglar alarm, scanners in television transmission, reproduction of sound in cinema film, in paper industry to measure thickness of paper, to locate flaws of holes in finished goods, in astronomy to determine we are using for electric equipment to determine opacity of solids and liquid, automatic switching of street lights to control the temperature of furnace, parametry, beauty meters to measure the very complexity of skin, light meters in cinema industry to check the light, for electric shorting, photo counting, and in metrology. Like that, we have various applications with the for electric. Thank you. Signing out.